So yes, there is still homework due today. 15.3, which was on like telling if a vector field is conservative and finding a potential function, things like that. Then the one on Green's theorem. Let's see. $15.4. That is due. It was to be due the Monday after, but I pushed it back to the Wednesday after. And then there are a number of assignments due during December, all the way up to the end of finals week, just to give as much time as possible for those to be done.
How many homeworks are left?
What?
How many homeworks are left after?
There are a grand total of 20 homeworks. So, counting today, there are 6 assignments remaining. 4 of those are due during the month of December. But all of those would be helpful preparation for the final too. Okay. And section-wise, for a couple sections ahead of a homework, I'm going to start 15.6 today, and then I won't be able to finish it. It'll be due. I'll finish covering that section next Monday. Okay. So squeeze in as much as I can. Okay. So this is now we spent a lot of time dealing with integrals over curves, and the way we describe curves is using parametric equations x of t, y of t, z of t. There's only one parameter because a curve is essentially a one-dimensional object. So if you took a line and just bent it. So now if you take a two-dimensional object, like a region of plane, and deform it, that would be a surface, and that would require 2 parameters. So first I need to discuss how we represent surfaces. And then how to evaluate integrals over surfaces. Okay. So the idea is you have a surface S. So does I use the letter C to refer to a curve? I use the letter capital S to refer to a surface. We have parametric equations. So you can think of a surface as a set of all points x, y, z, such that x, y, and z are functions of 2 parameters, which I'll refer to as u and v. And whereas with curves, our parameter t came from some interval from a to b. So the next logical step from that is all your points u and v come from some 2-dimensional domain D. So that is a subset of R2. Okay. Now, as an example, one of my favorite examples of a surface is called the Mobius strip. It's a rather strange surface that I can easily give parametric equations for. So we have x is, now there are many different ways to describe a Mobius strip. This is just one. So we have v over 2 cosine u over 2 cosine u. So in these parametric equations, u is playing the role of an angle. So y is similar thing. With sine u, and then z is v over 2 sine u over 2. And u being an angle goes from 0 to 2 pi, and v goes from -1 to 1. So I just easily could describe this using like polar coordinates, where v is like the r variable and u is like the theta. But I'm going to try to use u and v consistently in all descriptions of surfaces. Now, what I can do is, it's very easy to make a Mobius strip, and I'll tear off a strip of my attendance sheet. Aren't that many people here anyway. If I want to try to make it a even strip, this is not going so well. All right. So, in retrospect, I should have chosen a longer strip. Yeah. Okay. But the idea is you take a strip of paper and you twist it once, and then join the ends together. And yeah, I definitely should have chosen a longer strip, or a thinner one. Then you have a Mobius strip. And the idea is, this is a surface that only has one side. Because if I have an ordinary two-sided surface, like if I just undid the fastening of the two ends, and if I took a pen and drew on it, all the writing would be only on one side, this side or this side. But if I twist it and put it together, yeah, that did not go well at all. But there's also a picture of a Mobius strip in the notes. Okay. And if I were to take a pen and draw a line down the middle of a strip, at some point, what would happen is I'd wind up back where I started, which is not something that would normally happen. So with curves, we talk about curves having a clockwise orientation or a counterclockwise orientation. Or for most surfaces, there'll be a similar notion of positively oriented or not, where it's a clear notion of here's one side of a surface, here's the flip side. But Mobius strips is an exception to that rule. So not all surfaces have an orientation, but they can still be described using some kind of parametric equations. Okay, so that's one example. And here's a more normal example. In fact, this kind of surface we actually have seen before. A paraboloid. X is equal to 4 y squared plus z squared. And we'll let x go between 0 and 4. So if we look down the x-axis, starts at the origin, and then, so we have this paraboloid facing this way instead of a usual way that's usually facing up. And it ends right here at x equal 4, where at this end looks like a circle. I guess it's kind of like a Christmas ham or something. Okay. So, how would you describe this using parametric equations? Well, if you rewrite this as x over 4 is equal to y squared plus z squared, or better yet, if I take the square root of both sides, so I'd have square root of x over 2, it actually makes sense to use polar coordinates to model this, because we have this expression y squared plus z squared in here. So, so you could say that, so anytime you can write it like this, you can say y is equal to square root of x over 2 cosine theta. Z is equal to square root of x over 2 sine theta. So if you're able to express one of your variables using a sum of squares of the other two, then those other two you can treat using polar coordinates. So this, because this kind of expression in polar coordinates normally is square root of x squared plus y squared. But what is this equal to in polar coordinates? Like square root of x squared plus y squared. If you wrote that in polar, it's r. So this plays the role of the r. And therefore so does this, because they're equal. So you can think of here, this is our r. that goes in here. So that's a quick way to come up with parametric equations from a description of a surface like this one. And then x is just x. So in this case, really, you can think of x and theta as being your two parameters. Or another way to think about it, I could say this is u over 2 cosine v squared v over 2, or sorry, u over 2 sine v, and then x is equal to u. And then v goes from 0 to 2 pi. U goes from 0 to 4, because that was the limit on x, and x and u are the same thing. Now, I don't really care what variables you use for your parametric equations. If you want to stick with standard u and v, that's fine. Or if a surface is a natural description in terms of polar coordinates like this one does, then you can go ahead and just use r and theta, whatever you want to do. Okay. Now, one very important concept associated with surfaces is the normal vector. So if you're given a surface S that's parametrized by as parametric equations and parameters u and v, so you have r of uv. Now I use this for curves, so we have a function r of t. For surfaces, same idea. I'll use a function r of u and v, which has components x of u and v, y of u and v, z of u and v. Okay. So given a general surface, here's some common notation that we'll be using. R sub u, what do we normally use a subscript for? That's a partial derivative. It has that same meaning here. So this was a vector consisting of a partial derivatives of your parametric equations with respect to u. And then we also have a vector rv, derivatives of your partial derivatives of your parametric equations with respect to v. Okay. Now, it's similar to what we had to do for curves. For curves, we had x of t, y t, z of t, and we needed their derivatives. Now we just need more of them because we have two parameters instead of one. Now, once we have all this, the normal vector is, I'll use the letter n to refer to it, and that is the cross product of Ru and Rv. Now, does anyone remember, if you have two vectors, any two vectors, and you take their cross product, in this case getting a result n, how does n relate to these two vectors, like geometrically?
It's perpendicular.
It's perpendicular to both of them. So the idea is, here's your surface, here's a point on that surface, and these vectors Ru and Rv span what is called a tangent plane. Because remember, for curves you have a tangent line. For surfaces you have a tangent plane. So Ru and Rv at any given point describe that plane. Well, the normal is perpendicular to the plane. So therefore it must be perpendicular to vectors Ru and Rv that are contained within that plane. So geometrically this is what this looks like. Okay. So now I'll do an example. Given a surface, how you get the normal vector, because that's going to be very important for integrals. Okay. So given this surface, x is equal to u squared, y is equal to v squared, z is equal to uv. And u and v are assumed to go between 0 and 10. Right, so this is a description of your surface. So what you would do is, okay, so the problem is to get the normal vector n. So what you do is first you compute the two vectors that describe your tangent plane. So Ru and Rv, which are your partial derivatives with respect to u and v. So what are the partial derivatives of these parametric equations with respect to u, v? 2u?
2v.
No. 0, because with respect to u. And then lastly, v. Okay. All right, and what about for the other one?
0, 2v,
2v and
u.
yeah. Okay. All right. All right. In the notes I do this at a specific point, but we can get to that. We can do that at the end. So now, so the normal vector at any particular point on the surface, which is identified by a particular set of parameter values u and v, we can figure this out in general. And then if we have a specific point, we'll plug that in at the end. So n is Ru cross Rv. So we'd have 2u, 0v. At least there's some zeros. That helps. 0, 2v, and u. So, and this is my personal preference to write one vector on top of the other. You don't have to do it that way. There are many ways to evaluate a cross product. So you have, well, to write this out in general, so this would be yu zv minus zu yv for the first component. Then we have zu xv minus xu zv. And then finally xu yv minus yu xv. And then you can fill in the various partial derivatives from there. So first time around, we're going to have 0 and then minus 2v squared for the first component. And then we have 0 and then 2u squared for the second component. And then for a third component, we're going to get 4uv minus 0. So at any particular point on the surface identified by parameters u and v, that would be the normal vector. Is there any questions about how we get that? So it's an operation that will come up a lot. If we have a specific point, to let u and v equal 1, that means your point x naught, y naught, z naught would just be, you're multiplying these together, so you just get 1, 1, 1. So then the normal vector, fill in u and v equal to 1 down here, so you get minus 2, 2, and 4. Hold on. Sorry, that should be minus 2u squared. Okay. Now, with curves, we learned how to evaluate line integrals. First, the scalar valued functions, then vector fields. It's the same idea for surfaces. So in fact, I'm going to put 4 formulas side by side. There's 2 formulas for line integrals that we covered, for scalar valued function and vector field. And then there's 2 for surfaces that are broken down the same way. And you'll see the similarities between them. And no, these are not ones that have to be memorized, like on the final, but it would be a good idea if you're not spending all your time looking at the formula sheet. It's a good idea to be reasonably familiar with these things. All right, so I'll make a chart for you. So here's what we have. We've already seen for curves and then surfaces. Okay. So first item, what are your parametric equations? And then I'm going to call this vector of interest because for curves versus surfaces, there's different vectors that you need for the purpose of evaluating integrals. And then we have integral of scalar value function. And then finally we have integral of a vector field. Okay. So the parametric equations you have for a curve, so that would be r of t is x of t, y of t, z of t. T is in some one-dimensional domain, but what is a one-dimensional domain? The only choice you have is an interval, so we just do it that way. For surfaces, we have r of uv is x of, I really need a better piece of chalk. Okay. X of u and v, y of u and v, z of u and v, where u and v are in some two-dimensional domain that belongs to R2. Okay. Now, for curves, the vector of interest is the tangent vector. That is r prime of t. That's just x prime, y prime, z prime. Okay. For surfaces, though, it is the normal vector because there is no one vector. Here, this is the one vector that's needed to describe a tangent line. The normal is the one vector that's needed to describe the tangent plane. So the normal vector n is RU cross RV, where RU and R is defined as I wrote down earlier. So you still need whatever derivatives you have of your parametric equations. In this case, you have more of them. Okay. Now, how do you integrate a scalar valued function? What formulas may look very different, but I'll be able to point out a similarity between them. Okay, so that's what it is for a line integral of a scalar valued function. For the same kind of integral of a scalar valued function over a surface, you have the integral over your domain D, which is your parameter space. So it's a double integral because it's 2 dimensions. And then you have your function with your parametric equations substituted in. And then you have the magnitude of your normal vector. Okay. So I can describe both of these at one time. That it is the integral over the parameter space, so t over here, u and v over here, of your function with your parametric equation substituted in, whatever they are, for x, y, and z, times magnitude of your, this is just my term, it's not an official thing, vector of interest, the tangent for a curve and normal for a surface. So both, that sentence covers both cases. It's working in the appropriate number of dimensions. And we've seen how to compute a line integral of a vector field. So you're integrating from A to B, and you have your vector field with your parametric equations plugged in. And now you take the dot product of that with your vector of interest. Okay. All right. Now, can anyone, based on what you've seen from these three formulas, how these compare to one another? How these compare to one another? What do you think the integral, of a vector field over a surface should be? It all fits together in a logical way.
Your functions with your parameter substituted in time or dot product with your normal vector.
Yes. So you take a dot product with RU cross RV. And then, okay, what's missing? Let's fill in around this. That's the integrand.
And the double integral
Over
your domain or whatever D stands for.
your parameter space, your U of V domain. So du dv. Yeah, that's it. So here it's the integral over. So all of this applies down here, but instead of multiplying by magnitude, it's dot product with a vector of interest. Tangent in one case, normal in the other case. Okay, all right. So you see how all these formulas go together. And if there were higher dimensional analogs, which we won't cover, but if there were, this is how they would be handled. Okay.
That's very helpful.
Yeah, awesome. Okay. Now, also in both cases, my notes are out of order all of a sudden. Oh. Also in both cases, if you set this equal to 1, then that integral will give you the length of a curve. If you set this equal to 1, that would give you the area of a surface, which is abbreviated, bless you, A of S. So I want to mention that because that's the next example I'm going to do. So again, integrating 1 over whatever domain gives you the size of that domain. Okay, so an example involving area of a surface. Okay, so we have a surface S, and the way it's described in words is it's a part of a plane 2x plus 5y plus z is equal to 10. But you only want I mean, it's plane by itself is infinite. So we need to restrict it. It's a part of a plane that's inside the cylinder, x squared plus y squared is equal to 9. So what we have is, here's your cylinder, and you have this plane that's cutting through it. So this part right here where they intersect, that is your surface S. So, so for this cylinder, what sort of coordinates should we use to handle describing this surface that we've dealt with already? Cylindrical, yes. So in fact, for x and y, you can use polar coordinates. So I'll let x be equal to u cosine v, and y is equal to u sine v, and we'll let v go from 0 to 2 pi, and u, which plays the role of r, goes from 0 to 3, because that would describe all x and y that are contained within the cylinder. The only thing that's left is z. But z, you can take this equation and solve it for z. So that's 10 minus 2x minus 5y, but then you can fill in what x and y are. So 10 minus 2u cosine v minus 5u sine v, and then you're done. Okay, then you have the parametric equations of your surface. So any questions about where the parametric equations come from? So often if you use polar for two of the variables, then you can just use the remaining whatever equations you have to solve for the other variable. Just like with a paraboloid, it makes sense to express y and z in using polar coordinates, and then you can figure out what x is supposed to be from the original equation that you're given. Okay, so now we need Ru and Rv. So what are the partial derivatives of these three equations with respect to u? What are partial derivatives of these equations with respect to u? So we need xu, yu, and zu.
V cosine v
Or no.
cosine v
Cosine v.
sine v.
Okay.
It'd be negative 2 cosine v
And there's one more term.
minus 5 sine v.
All right, and then the next one we have x, all the partial derivatives with respect to
V.
v.
Which is gonna be negative cosine v times sine.
All right, so like this with respect to v, u is a constant.
So sine
So negative u sine.
Yeah,
Negative
minus
u.
u sine v. Okay.
And then negative u cosine. Or
Yeah.
u cosine.
u
u
cosine
cosine
v
And then you can see where it goes from here to sine v minus 5
cosine v.
cosine v. Okay, and then you have to take the cross product of these. Very tedious. Fortunately, you get a lot of use of sine squared plus cosine squared equals 1.
Why didn't you go with the two sine v on?
Oh, sorry. Yes, they did. Yeah, sorry. Differentiation is no different than what happened over here. Are we good? Okay. All right. So it turns out that the cross product of the two turns out to be quite a bit simpler than either of the original vectors. So I won't go beyond it here because of time, but something you should check. And what you get is 2u, 5u, and u. again, because a lot of cosine squared plus sine squared equals 1 happening. So then what you can do is, for an area integral, you need the magnitude of this. So the magnitude, we use square root sum of squares of each of the components. So 2u squared plus 5u squared plus u squared. So what would that give us in the end?
30u squared?
Uh,
The square root of 30?
yeah, square root of 30u squared. Yeah, so under the radical you have that. So 30 square root of 30
U.
times u. And technically I should say absolute value of u, but u is only between 0 and 3, so we can just leave it as u. So now what you can do is evaluate the integral, the area of the surface. It's the integral over the parameter space, so 0 to 2 pi in v, 0 to 3 in u, magnitude of your tangent vector, normal vector, vector of interest, du dv, and now you can fill this in up there. So you get, well, actually you can split this into two integrals because the limits are constant and your integrand is just dependent on u. So what we get is 2 pi over here, square root of 30 from the constant. Here you get u to the 4th over 4 with limits 0 and 3. Whoa.
Huh?
Hold on.
Square root
Yeah.
of 2.
I got 3 in the brain. Okay, so then these 2's cancel out. You plug in the limits and you get 9 pi times the square root of 30 units squared, so that's the area of that surface. Okay. The questions, especially in the setup. Certainly pretty tedious. Well, there will be a few problems in the final involving surface integrals of some form, because one where you're doing something like this for area of a surface, another where it's surface integral of a vector field, which we'll see next Monday. Also, theorems that we'll see, like Stokes' theorem, that's coming up in the next section, involves these kind of integrals. Okay. Does anyone have any homework questions? While you're looking, I'll pull up this assignment. Anybody navigating to one, or we good? Or, okay. Okay. I want to point out some special cases of this formula for area of the surface, where parametric equations have a certain form. All right, this is case case my camera wasn't pointing in the right direction for this screen for anybody watching. All right, but this is that example that I just did in the notes. Okay. Suppose your surface has these kind of parametric equations.
What does that say?
Suppose S has parametric equations. Well, you can really think of Z as a function of f of xy, which is how we described some surfaces way back when we were doing double integrals, like volume under a surface. Those are not parametric equations, but they convert very easily to parametric equations. X is equal to u, y is equal to v, and z is equal to f of u and v. And we have x and y, which is the same as u and v, are contained in some two-dimensional domain D. Okay, so in that case, if you were to work out what the normal was, is RU has a very simple form. It's 1, 0 df du, which is the same as df dx. RV is 0, 1 df dv, which is the same as df dy. And therefore the normal vector is just, okay, that's unfortunate, fu, fe, and minus 1. Which is the same as fx, fy, minus 1. So that means that the area of S is the integral over your parameter space, where your x and y are coming from. And if I express this in terms of just x and y, we have 1 plus partial of f with respect to x squared plus partial of f with respect to y squared dx dy. Now, whether this integral can be worked out does never matter, but at least the setup is a lot simpler in that case. So if this happens, this is how your surface is described. Just jump directly to this. You don't have to do any cross product stuff. I've done it for you in this case. Okay. So, for example, z is equal to 1 plus 3x plus 2y squared. And your domain D is the triangle in two-dimensional space with vertices 0, 0, 0, 1, and 2, 1. So the way you can describe this is, so the area of S is the integral. We can go from like 0 to 1 in y. And then for x, so for each y between 0 and 1, x is going from here to here. Now this is the line, y is equal to x over 2, but I need x as a function of y. So 0 is my lower limit in x. What should my upper limit be? So if I take this and describe x as a function of y. Yeah, you just solve this for x. X is equal to 2y, and that describes my upper limit. I'm integrating here with respect to x, therefore my limits must be x values. Okay, and then here your partial derivatives, dz dx is equal to 3, and dz dy is equal to the derivative of this for y. So now I can have the integral of 1 plus 3 squared plus 4y, the whole thing squared. Okay, that's your integrand. And set it up this way, y is the outer integral, x is the inner integral. That way, this integral could actually be evaluated. Otherwise, it'd be real pain, or perhaps impossible. Okay, and this is worked out on page 133, 34, where what you do is you can move this out to here because it only depends on y. Then when you integrate in respect to x, you get 2y. And what you get is a chance to do a u substitution to work out the integral. Okay. Very last thing, a couple other special cases. A surface of revolution. You may remember in Cal 2, you dealt with, for instance, taking a function and rotating it around an axis, x-axis or y-axis, and you did the disk method, shell method, and you computed volume. Well, in those examples, you always did volume, never area. Here you can do area. So you revolve a function curve y equals f of x, and x is between a and b. If you revolve it around the x-axis, then you get these parametric equations. X is equal to u, y is f of u cosine v, z is equal to f of u sine v, and then there's a your normal vector, if you work it out from all this, is just, this is the magnitude. So the area of a surface of revolution is the integral from a to b, and you have 2 pi, and then you have f of u square root of 1 plus f prime of u squared du. So everything I've shown in a more general case, for this special case, works out to be this. But this is around the x-axis. That's your formula. But if you take the same curve around the y-axis, so here you have your curve and you revolve it this way to get a surface revolution. But here if you take the same curve, y equals f of x, and you revolve it this way to get a different surface of revolution. Okay. Then what you get is area is a similar formula, 2 pi integral of a to b. And instead of f of u, you just get u. And those in both cases, the derivative is squared. Okay, so those are the special cases, and these may or may not come up in the homework. Okay, so you don't have to do any cross products in that case. Okay, I'm sure I'm past time, so happy Thanksgiving, and we'll do more of these fun surface integrals on Monday.